Okay, good morning. So this week I'm going to cover chapter 9, which is on main memory. And so this chapter is about a couple of different topics. One is how code is loaded as program image from maybe disk or flash into main memory so that it can be run. And this is needed for supporting like OS loading a program into memory, and actually what happens when you have multiple programs that must be running concurrently. And as part of this use of memory, whether it's for program or for data, you come into the issue of, well, just where do you place it? And do you have a big enough chunk of memory for this purpose? So there is this concept of what's called contiguous memory allocation. Because when you write your program or compiler generates a program, usually it assumes that the memory just goes from some starting point and up until some ending point. So you have a contiguous, at least range of addresses you may be using. Now, whether or not you actually manage your memory in the same way, that's a different question. So contiguous memory allocation means I actually try to go to physical memory, and if the program says contiguous range, I give it contiguous physical memory for it. And that can be problematic. And so a solution to address this problem of a contiguous physical memory allocation is called discontiguous memory allocation. There's actually two schemes, one called segmentation and the other called paging. This textbook, I think, used to address both segmentation and paging, but I think in this latest edition, they just took away segmentation, or at least moved it to another chapter, because really people don't use it anymore, or not much anymore, even though the mechanisms are still there. So we're only going to be considering paging as a way of doing discontiguous memory allocation, but that memory actually means physical memory allocation. So logically, you see contiguous range of memory, big chunk, but then physically it's broken into different physical blocks called frames. And then through mapping from logical memory to physical memory, that's how it achieves this discontiguous memory allocation. A lot like your file, right? Sometimes you can have a huge file, several gigabytes, but then is it on disk all contiguous? No, it's actually spread out over different disk blocks. Somewhat of a similar idea, but disk does it differently. And to do paging efficiently, you really need hardware support, as well as some data structure. So the data structure for this, for paging support is called page table. Now, page table is a table, really. As you might think, you index into a table, maps from the logical or virtual page number to a frame number, which is physical page, so to speak. And this can get to be a big data structure, almost too big. And so there are different solutions to that. And we'll mention a little bit about swapping. Now, the term swapping, at least originated in the Unix community. That actually used to mean that you take an entire process and move that entire process runtime image, including its code, its data, to disk. But that seems pretty drastic. So modern OSs actually don't do swapping in the traditional Unix style. Instead, they do a special version of swapping, and that's called demand paging. And that's a related topic. We'll only mention it a little bit because we happen to be talking about paging, but then that will be a topic that we'll revisit later. Okay, so that's kind of a quick overview of what I would like to talk about for chapter 9. And there's also case studies of how different architectures, different OSs handle this, and we'll only touch on the very brief part because I think those are really just highlighting some of the concepts we'll be presenting here. Okay, so the first topic has to do with loading a program image from some disk or flash into memory so that it can be run, right? the idea is not so much like embedded system. A lot of embedded systems, you write your firmware, program it into the Flash or the EEPROM, or actually Flash more often now, and then you just run in place. So, and usually that's supported with what's called NOR flash as opposed to NAND flash, which is what you use on your SD cards and most of these SSDs. And NOR flash allows you to do byte addressing or word addressing. And that is a good match for what's called direct execution in place. But that's not usually the case with general purpose computers. And with general purpose computers, what you need to do is, well, you follow mostly von Neumann architecture. That means program and data reside in the same address space. And how does a program get there? Well, somebody has to load it in, right? So the loader part of the OS is what actually reads the program image, puts it in memory, and then jumps to it. Okay, that's the loading part. Now, so when you have this kind of thing, it really goes beyond what the CPU can do. Why? Because the CPU, what it does is the architecture only has instructions for you to like read and write these registers, read and write your main memory. But anything beyond that, you actually have to go through I/O. But then those would not be something you do directly. You have to do it through I/O instructions or some other memory mapped I/O and so forth. Okay, so so this would be the job of an OS or a loader to do this. And the OS or loader would have to then manage, okay, I now read this memory, that's the program image, from disk into memory, but then where do I put it? Well, OS itself takes up space, right? And so you can say, well, wouldn't I just create a new address space just so that I can deposit the memory into that address space? Well, logically speaking, that may be the case, but physically, you still have to put it in physical memory somewhere, right? So where do you put it? As OS is developed over time, there's different schemes that have been tried. And even to this day, different schemes are used just because depending on what's practical, you do different things. And it also depends on whether or not you need to support swapping, which is something I mentioned on the previous slide. Do you do swapping? That is, do you ever get into a situation where you need so much memory that you have no option but to kick out some process temporarily? That is, take that entire image in the memory and put it on disk so that you free up memory. Well, if that's ever the case, then you may need to think about, well, just where would I locate the program in memory somehow. And another consideration is with the multiple processes running, you do want memory protection. You don't want them to be able to rewrite each other's memory unless they say, I'm going to do sharing. Then you only restrict the sharing in those restricted parts of the memory. Okay? So what do people do? Well, the very first scheme is how do you define your address space? Well, address space is not necessarily, say, if I have 32-bit address on my architecture, then I automatically get 4 gigabytes of memory, right? 2 to the power of 32. No, that's actually not automatic. And especially in the older days, these program images are quite small. So you could actually fit multiple processes all in physical memory at the same time. Let's just consider that case where you have enough physical memory, and this is showing physical memory, right? And so what do you do? Well, you would like to be able to load in the program images as well as the data space for different processes. So here it's showing OS starting from address 0 up to some point, and then after OS, you have the what's called address space for process, the first one, the second process, third process, 3 processes, and then you have free chunk in blue at the bottom there. And so each process, even though your pointer is 32 bits, you might only get a range. So it might say, well, like the process in the middle only gets to address memory between address 300040 and up to, but not including 420940, right? So this process, its address space is within this, even though you could easily specify a pointer of 0, a pointer of FFF or something, right? And so any attempt to address anything outside its address space, well, OS would catch it, right? So OS would get it, the hardware should generate a trap to the OS, then OS handles it and gives it some like address access violation. Oftentimes you see this in the form of segmentation fault, right? So OS needs to ensure that every memory accessed by the user is within its defined address space, even if it can name addresses outside its space. Okay, so that's the simple scheme of base plus limit register. That's one of the earliest forms of doing this kind of protection for multiprogramming, right? And this is easy. Why? Because you could imagine hardware to do this check every single access. So what would the hardware do? Well, every time memory load or store instruction is issued, well, addresses come down, right? So you get a piece of address. Now this piece of address could be part of this memory access pipeline. And so it goes through two comparisons. And you've probably taken logic, right, digital logic courses where you can imagine how you would do this comparison, right? So what do you do with a comparison? It's greater than, equal to, less than, equal to. Well, right, you could, you know how to build an adder. You know how to do complement, 2's complement, and then do the add, right? So then you can check if the result, the sign bit, right, for this. And so you can imagine straightforward hardware flows through, hardly takes any time. So that way you don't have to execute separate instructions just to see if your address is within range, right? So one is check to see if it's at least as large as the base. Second check if it's at least base and above. Check to see if you exceeded the limit, base plus limit, right? And then if it's still less than the base plus limit, then yes, it's a good address. You're within the address space. Go ahead, access memory. If not, well, hardware can easily set a bit and generate a trap. Always takes just like any other interrupt, right? And so now the program's location in memory can be an issue, right? So because, imagine how we did SDCC. Yeah, you compile or you wrote your code, right? Or a lot of times you remember from beginning we did org 0 and then assume that you can start writing code from there. But can you really? Well, remember the early part of your memory, at least program memory, is your interrupt vectors, right? So that means if you ever use any interrupt or support any kind of OS preemption interrupt-driven I/O, well, that part is out. You've got to start your program somewhere else, right? Yes, you could do a jump from location 0 to the actual starting point of address. So whatever the case, when we did whether assembly programming or SDCC, we kind of fixed that address, right? But is that going to work out if you need to support dynamic, or I should say loading a program into memory and then execute? And actually, how do you load multiple of them, right? Aren't they going to conflict? Aren't they going to fight over, hey, I want to start from address 23, but this other program also wants to start from address 23. Aren't they going to overwrite each other? Well, that may be the case. It depends on how you support what's called relocation, okay? And when do you do relocation? So there's actually many different schemes. There's compile time, what's called binding, load time binding, and execution time binding. What does binding mean? Binding means there is some address I want to access. And all I can say at some point, whether compile time, load time, or execution time, is relative to the start of my program. So whatever my program is, or whatever this module is, keep that as some kind of variable, right? And so depending on whether you've fixed that offset at compile time, at load time, or at execution time, or determine it, then you may have to do different things. When we did the SDCC, or that was called compile time binding. Why? Because by the time we generate the program image, all the memory references are already fixed. You already know if I'm going to put my variable x at address 32. I mean, when you look at SDCC, it's always 32, right? So at compile time, or actually compile and link time, that's already fixed. But that doesn't have to be the case, especially if you have to support multi-programming, because I might say, well, it's location 32, but I want to allow the possibility of OS loading my program into maybe a different part of the memory. So 32 might not be 32. I only think it's 32. But in reality, depending on where OS puts me, right, in physical memory, then that 32 may be added with an offset, right? Who adds that offset? Well, it could be the loader that adds it. What does the loader do? Well, the loader reads the image from disk into memory. But as part of it, writing that image from disk to memory, it looks through those addresses and say, hey, that looks like a pointer to me. And because I'm putting it at offset 1000, every time you say 18, address 18, I'm going to add 1000 to it. And it writes it directly into the memory, okay? So when you run it, yes, when I programmed it, I thought address 18, but the program that's actually running it, it's been modified by the loader so that it'll execute address 1018 instead of 18. Okay, so the loader has that opportunity to modify certain parts of the program, especially the address part. But once it loads it in, it does the modification, it stays there. Okay. Now you can say, well, that's not all that flexible. What if at runtime I want to be able to say maybe I shift this program around? And why? Well, later you'll see some examples. Then yes, then in that case, it wouldn't be the loader. You need additional support, right? So then execution time, the program image still says address 18, but it depends on where its base is. At runtime, that 18 is added to the base by some hardware, hopefully, right? So that way, it's more efficient, kind of like what you saw with the address support for checking segmentation. So anyway, so you do have different options for what's called address binding. That is, your program initially, as defined in the program image, may have its idea of where memory locations are, but those actual locations could change. Could be changed or could be determined either fixed at compile time, or the loader, as it loads that image into memory, it modifies all those addresses. Or at execution time, loader wouldn't modify those, but then every address you issue gets modified with different offset and so forth. Okay, so that's a step of address mapping. So the address binding could be done in different stages. Okay, so first, compile time. As I said, you're used to this, SDCC 8051 SIM. We only run one program. It's all built at compile time. So everything is determined at compile. Well, compile time includes the linker, right? Because the linker, you may compile them separately. And if you ever have the guts to look at the REL file, the relocatable files, you see that it doesn't actually fix all the addresses, right? I mean, unless you say data at address 32, yes, you already hardwire that address, but then you have other variables. Well, those haven't been assigned, or even the code addresses haven't been assigned, right? And those are not determined until you do the linking. So the second pass of SDCC. You could do SDCC minus C, that generates the REL file. Or in most other Unix systems, minus C gives you the .o files. Those are relocatable. So they haven't committed yet to the actual final address. But at the time of linking, that's when it starts lining things up. And this is like how much, and this is how much, and then says, oh, because now this module comes after next, then I need to start my address so much later, right? So all these other ones are relative to the start of their module, and then those addresses get filled in by the linker. Okay. Then in your executable image, everything is already determined, and as you run, whatever you see in your executable image, the address 18 corresponds to address 18 on the machine, physical machine. So when you debug, that's you know exactly where to look for, right? So that's compile time binding. Why is this a good idea? Well, you know exactly what's going on. Nobody gets to mess things with you, and no additional hardware needed. Very simple hardware, streamlined. I mean, what could go wrong? Well, not as flexible, right? So this is compile time. So the linker basically fixes the addresses, and then that way it's exactly what you get when you run. And this is actually the scheme with MS-DOS. Everybody remember MS-DOS? So before Windows, that's how Microsoft's first OS. Well, they basically didn't have that when they told IBM, and then they went and bought that from the company in Seattle, and then said here, and they made some changes and called it MS-DOS. And so that was text-based. It ran a single program at a time. When you log in, you get a shell, right? And then you still have the CMD on Windows, but then that's a very different one now. And that runs one program at a time. So that allows your compiler to generate fixed location, because it knows where the OS resides, how much space the OS needs, and then when it loads, it's at that location, right? So then you have the disk image has the base, and the linker already adds the base to the address. So even though the compiler compile time, it says offset from 18, and as soon as the base is defined, linker knows so to add 1000 to 18. So from the program image, you can already see that's the location. Okay, loads it in. The loader doesn't have to do very much. Doesn't have to do any translation. Just loads, and that's it, and it runs. Very simple. But it only allows one program at a time. Why? Because if you try to load another program, loads into that same location, covers over, and then that's it, right? So you can't do multiple. But what if you have to do multiple? Well, then you would use a different offset, but then that might mean relinking your program, which is more of a hassle, right? It's like, what? Every time I have to run a program, I have to make relink with a different base so that it doesn't override the other program. That doesn't seem like a good idea, right? That kind of defeats the purpose of having an OS in the first place. So, but that's a very simple scheme, right? Compile time, address binding. Now, you can make it more flexible, so that way the base is not fixed until, or not known until loading time. So you may have one program, and first the OS says, okay, when you start loading, start from address 1000. Next program wants to be loaded, well, because it knows how big that memory image for the first process is. Then it says, oh, well, next one, you can come in at address 2000. So it says address 2000. So the loader, when it reads in the program image, it sees, oh, it's .bs, that's a base address, and then plus the offset 18. But now I know, right, at the load time, now I should start at address 2000 instead of 1000. Then it rewrites that address by adding the offset 2000 into it. And maybe next time, after loading this, the base address becomes 3000 again. Now next one 4000, right? So then it does different things, different modifications, depending on the order in which the program may be loaded into memory image. Okay, so that's what the loader can do. It could just make those target as small changes. Every time you have a memory reference, it adds it in. And in fact, it doesn't necessarily have to be data. It could be the routines. You have like print, you have your own function call. Those would also be the addresses. So it adds the base to all those pointers. Okay? So that way, yes, you could actually support multiple things. And the loader just gets slightly more complicated, but not very complicated. It just has to scan. But since it has to read in the entire byte anyway, just quick scan, quick add. And then that's not very difficult. So that is a quick, cost-effective way to do this, right? To do load-time binding. But once the loader loads it in and rewrites those addresses, it's fixed for the duration of that process, right? And then goes out. Next time you load the same program back in, it may be a different base, right? The loader would then rewrite those addresses again. Now, execution time binding is more flexible in that it says, well, loader, you don't have to actually do the rewrite. You just load it into whichever address you find suitable or you can fit. And but you rely on hardware to do that base address adding for you. So you keep the offset at 18. And then every time there's a read or write, or even jump, then hardware says, well, I already know the base. Let me add that in. And so the physical address actually is different from the logical address. Logical address is what your program thinks is accessing. It thinks address 18. But in reality, hardware maps the 18 to 1018 or 2018 or something, right? So is that okay? Well, most likely okay, because the program couldn't really tell the difference anyway, okay? But then that requires your hardware to do a little bit more work, and well, it's actually not too difficult. I mean, the processor itself is way complicated compared to having a little bit of adder, right? And so this kind of thing is how most general purpose OSs do. They don't actually bother with the loader going in and scan all the addresses and then modify them. But then, that's still done in some cases, especially embedded systems. There's some embedded systems, I think, or especially wireless sensor nodes, they're very constrained, but they want to support this kind of thing. And so their loaders can go in and add the offset, the base to the offset. Okay, so in this case, the loader still loads in the image. It's all logical address. So if it's offset 18, it's offset 18. And then the base then is known by the hardware, right? The base, the 2000. So when this address is issued from CPU to memory subsystem, the offset is added to it and then before going to memory. The program itself has no idea, doesn't know. It still thinks it's address 18, but in reality it's address 2018 or somewhere else, right? And so this is one very simple form of hardware translation to help this kind of what's called execution time binding. Okay? And that works both for code address as well as data address. And because we're talking about von Neumann architecture anyway, they're really not all that different. So now, once you start doing this kind of thing, then the logical address and physical address can be different. Okay? They could be the same, but they could be different. Most likely they're different. So for compile time, logical address is the same as physical. That is, when my program says 18, physical address 18. No questions asked. Load time, well, the program may say one thing, but it kind of allows it knows the possibility of changing. So by the time it's loaded into memory, the loader already does a modification. So as it's running, all it can base on is the image in memory, not the image on disk, right? So then the program thinks, oh, the loader already changed my address from 18 to 1018. Then I'm going to do it, read and write. But then that 1018 is physical 1018, not just logical. But if you did the execution time binding, like I said, the program still thinks I'm doing address 18, but it actually physical address, it could be a different one, right? So in the execution time binding, logical address and physical address may be different, and most likely they're different, okay? So, so that's the difference. And in fact, for most of what OSs do, that execution time kind of mapping is important. And so we will start to make a distinction between the logical address and the physical address, okay? And another word for logical address is a virtual address. Although some people feel virtual, really, if it feels like not so real, well, okay, fine. But saying logical makes you more comfortable, yeah, you can say logical address. But that, when you talk about virtual address, is really the same as logical address. That is what the program thinks it is actually accessing, right? Is that, and a lot of times that's really all that matters for program. Okay, and so for supporting this type of memory mapping, you do need hardware support. And the general term for this is MMU, Memory Management Unit. So obviously on 8051 there's not an MMU, no need, it's always the same. Physical, logical address, always the same, no need for MMU. But for most systems that need to run an OS, MMU is assumed. And it could be very simple to very complicated. Okay, and then there's different parts of MMU. And so really the whole purpose, well, several. One is to do this address translation. So to do that, minimally, you need some kind of base register, right? And now it's called relocation register because it basically sneaks in that addition of your logical address to the base address. And then, so that's minimally, that's what it has to do. And who gets to set this relocation register? Well, obviously the OS, because otherwise, if you let the user code set this, it could change it to whatever it wants, and then you don't lose the protection, right? And this is calculated on the fly, it's part of memory pipeline, every single access. So your user program doesn't even see this, okay? Now, different architectures may support different base relocation registers. Why? Because it may need to support, for various reasons. One could be like one for OS, one for user process, or maybe one for I/O, one for whichever, or different kinds of things. Could be one for code, the other for data, right? And there's different schemes, so lots of variations. Different processors may do it differently, but it's all under the concept of MMU. Okay, now we want to go a step further, which is, do you really want to load in your entire program image to memory before you start running? Okay, so one might say, why is this even a question? Why not? You want, right? The program code should already be in memory, so when I run, it has a valid place to go to, right? Well, but these programs are getting bigger and bigger, right? I mean, when's the last time you saw, like, you install an app, several gigabytes, right? Do you really want to wait for it to load in the entire 4 gigabytes before you can start running? Probably not, right? That's going to take a long time. And besides, have you ever heard of like a 2080 rule or 1090 rule? So, I mean, there's different versions of this. Like 10% of your program is run 90% of the time. The remaining 90% of your program is run for less than 10% of the time, right? So maybe it's better if you load in the 10% you're most likely to run, and the other 90% you load in as needed, and then that way you get started running much quicker, right? And so dynamic loading is based on the concept of I probably don't need the entire program image to be loaded into memory before I can start running, right? And if I ever jump to a part of the program that hasn't been loaded, well, just load it at runtime. You take a trap, just like an interrupt. The program, we wouldn't even know it, right? So the program, well, when it jumps there, well, OS could take over, and then loads it in. That's one way to do it. But in fact, you don't even have to do that. OS doesn't even have to get involved. What you can do is, your program can do that itself. In fact, it's not even something that's so privileged. And so the OS actually just had to provide the library support, right? And your program can be structured in a way to check, hey, is that call in memory? If not, make a system call, load it in, and then jump there, right? That your code can manage this. That way, it's even better because the OS might not even have that knowledge. Right? OS is taking its chance. And whereas if you do it, your program is probably much more knowledgeable about itself. So then it can even schedule these dynamic loading over time and then plan things out. That gives you the best user experience. So you run something, hey, it shows up and starts running, great. How does that work, right? Well, they may rely a lot on dynamic loading. Okay, so bring in only the part you need to get you started running, and then rather than the entire image. The other parts could be brought in over time as needed, on demand. So this way you get better memory space utilization. If you don't ever call some routine, it's never loaded. Great, you don't do extra work. Right? That's great. And so this is especially useful when you have large amount of code, okay? And a lot of that is infrequently used. Okay, so yes, OS may help, but OS doesn't have to do this. Your code, user code can do this. And in fact, you can do this in C by calling this API, that dlfcn.h. And what does it do? Well, so in case, I mean, you might be able to do this, like cosine function. I mean, do you really need to use the cosine function that much? Well, depending on your application, right? So if you rarely use it, you may be able to even do dynamic loading for that. So that way, you just define a function pointer to cosine, and this is the type signature for it, right? So it takes double as parameter, returns a double. And what you do is, if you want to load it in, you could do the path, and then in fact you could do the lazy part. And in fact, some library is not linked automatically. So like math library is actually not linked automatically. So if you want math library, you do -lm, right, as part of your linking stage of CC or GCC. But you can still load that in dynamically. And so you do the DLSim, and that loads the code, and you could specify different options, and then call it. Then that code is loaded in, so you can call it, and you can even close it. So dynamic unloading. So you can imagine this, right? Initially, your program only gets the function A loaded in, and then wants to call B, B gets loaded in on demand, and then once called C gets loaded in on demand. After C ends, you could either keep C around or you could unload it. Okay, so that way it allows you to free up memory for code, and that's useful. And in fact, code is assumed not to be modified. So when you release it, you don't actually have to do any saving. You just update its current status, and then next time you can check if that pointer is valid and all that. Right? Now, what's a problem with dynamic loading? Well, so we know its advantage is faster, shorter response time, but if you keep doing this without coordination, what could happen? Well, you could load in multiple copies. And each time you load it in, it takes up more space. And this could happen either within the same process or maybe across different processes, right? So you have another process also dynamically loads in cosine. But guess what? Your address space is protected from their address space. I load in cosine. The other process doesn't know it? No, it's in my space, right? How does the other process possibly know I loaded in cosine? It couldn't even see anything I do. It couldn't even address any part of my space. If it tries, it gets a trap and then reports segmentation violation or something like that, right? So that's a problem. And if everybody dynamically loads, you can have like 20 copies of the same library dynamically loaded in. And so that kind of defeats the purpose, right? So that's what happens when you have static linking plus dynamic loading. You could save disk space, but then you could load in multiple copies, okay? Because every time you do the linking, it already specifies some address, but then it's not known to another process, or you have no way of checking that, right? So dynamic loading, if done just in the straightforward way, could have this problem of redundant copies, right? And that's a waste because your code is not supposed to be modified, but then you keep multiple copies of read-only data. That's silly, right? So that means you need to somehow expose this knowledge to the runtime system for this to work effectively. So that's where dynamic linking comes in. Dynamic linking basically says, well, the linking or the resolution of address for this library is done at runtime. Okay, so so as you run, well, what happens is then the dynamic linker gets involved, and it offers these stubs. So when you call the stub, and the stub is what checks, hey, is there already a copy resident in the memory? If so, don't load another copy and just allow it to use it. And this is possible because you can impose certain access restrictions, saying, well, this is code, nobody gets to modify this. Well, other than OS. OS is the only one that can modify, but then everybody read only. So, and because this is not any secret, everybody can jump to it. And in fact, you can even allow execute only without reading. That's OS or hardware, OS plus hardware combination can support that. So that way, it only will it'll enable this kind of sharing, reduce the redundant copies in a result of dynamic loading, right? So the stub is that kind of first entry. It's responsible for checking if that library is already loaded in. If so, don't load another one. Instead, go through it and use the existing copy, right? So it can replace itself with the address of the routine and then execute normally. And so this sounds good and all until you need to consider, well, what if I have software update? The software update may update one of the dynamic loaded library, and on Windows it's called DLL, right? And then there's other things. If it's in the middle of software update and you don't shut down all the other programs, they keep running, well, what happens? Then the new executable, new DLL comes in. Can you just overwrite the old one? Hard to say, right? Because that other program is still running, and it may unload and load during its time, but it better be consistent so that the next, it's still running before the process dies, right? It unloads and loads. It better come back with the same exact image, same version, instead of you load, unload, and then next time it's a new updated one that comes in. That could be problematic, right? Because the new DLL may make other assumptions or make different access restrictions, may require different new settings and all that, and it's going to be a mess. So to support dynamic linking in today's environment where you actually have lots of software update, you may need to support versioning. So it's not just loading a particular library, you actually need to know which version. And you may need to do some kind of hash key or the date and all that, just to make sure that's the case before you can safely execute that. All right. So of course, after the process is all gone and nobody using it, then you can safely remove the older version. Okay, so dynamic linking allows you to have one copy of the code in memory for sharing, and the mechanism it does so is with a stub, right? And that checks to see if the shared library is in memory. If so, load it. If not, if not, then load it. If so, then execute. And this is well, I mean, you probably know from DLL on Windows, and certainly on other architectures. They did it way before Windows did, but Windows seems to have the most popular name DLL. Others could be Dynamic Library or .so. There's different names for this. Right? Okay, so that was really on how code is brought into memory. Now I'm going to talk about contiguous allocation, and this could be for code or it could be for data. Before going to contiguous allocation, this here really means contiguous physical memory allocation, even though when you read it, they just say contiguous allocation. Okay. So now memory usually has, you could view, there's the OS part and the user processes. Now you kind of saw that image earlier, right? OS part, where would you put the OS? Lower memory or higher memory? Well, traditionally you would put in lower memory. Why? Because when you boot up, you tend to start from your reset vector, right? And then that's usually at address 0, and your interrupt vectors are usually at the lower part of address. That's just how most CPUs do it. And so the natural thing to do is, okay, well, since I have to start from beginning, let me put all of OS in one chunk. So OS tends to reside in the lower part of the memory. And that's been the case for a long time. But Windows and Linux place OS in higher memory. So, okay, fine. Doesn't really matter. So now, but the key point is you need a chunk of memory, big enough chunk for putting the user processes, right? So user processes are held in, well, not necessarily high memory, but maybe behind OS, or well, you could say in between, right? And each one has a single contiguous section of memory for this kind of contiguous allocation. But even there, you can do what's called fixed partition versus variable partition. Why? Because do you do it just to the exact size you need? I mean, process 1 needs 1 megabytes. You give 1 megabytes. The next process that comes in says, I need 1.5 megabytes. Do you just give it 1.5 megabytes? Or do you round it up to 2 megabytes? Right? So what is your basic unit? Is it to the byte? Well, probably not, right? And well, fixed partition says, well, my minimum unit may be 1 megabyte. Okay, so if you need less than a megabyte, I give you 1 whole megabyte anyway. Yeah, I wasted a little bit of memory, but I don't care. But another scheme is, well, I may want to not have this kind of basic unit, right? So if you tell me 342 bytes, I give you exactly 342 bytes. And then next one needs 1018 some odd number, and you get 1018 some odd number bytes. And that would be variable partition. Okay? So what would be the advantages and disadvantages? So if it's a fixed partition, that means you get loaded into a partition, and hopefully that is enough for fitting your entire program or entire process. But then by partitioning this up, then what happens? then, well, memory is so much, and we're talking physical memory here. So you only can divide that in so many different ways. So your degree of multiprogramming is limited by how many partitions you can have, right? Because the assumption is you can fit all your processes into some fixed partition, right? Now, variable partition, what happens? Well, yeah, first couple ones you may fit because you start lining them up, and then but processes come and go, right? They get spawned, they die. And then what happens when they die? They free up some memory. But then it's like a few 342 bytes in between. And then you free up here and free up there. Pretty soon, your free memory is all scattered. You don't have one contiguous chunk. And then next time a process comes in and I need 782. Well, yeah, I have lots of little pieces. I have 100 bytes here, another 100 bytes there. But they are scattered all over the place. They're not in one place, and then sorry, can do. Even though you have enough memory total available, they're not all together, and so that's the problem with holes, right? And so that's an example of what's called fragmentation, because these free memory chunks are scattered all over the place, and so and if you need contiguous memory allocation, you can do it.